Assalamualaikum and good day. My name is Muhammad Amirul Farish bin Yassin and my metric number is 081933. Today I will briefly explain what a parallel algorithm is. A parallel algorithm is a computing method that performs multiple operations at the same time using multiple processors. It increases efficiency by dividing large tasks into smaller subtasks that executing them simultaneously. One common example is the parallel merge sort. It's a modified version of merge sort where the divide, sort and merge steps are executed concurrently. Here's how it works. First, the array is split into half. Each half sort in parallel using separate tree or processor. Then the sort part are merged together. Still in parallel, each processor handle a sub-array, and once sorting is done, the results are merged in pair. This saves a lot of time compared to sorting everything one by one. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Ismail Aziz Amir Talib. Number metric is 081430. Today, I'm going to present and explain about work and span on parallel merge sort. So, what is work on parallel merge sort? It's a total number of operations performed by the algorithm. It represents time taken if executed using one processor and used to measure the overall computational effort of an algorithm. So basically, work is a total of number of operations an algorithm perform. Imagine running everything on just one processor. It tells you the overall effort required. So let's jump to the span on parallel merge sort. So what is span on parallel merge sort? It's the line of the critical path and algorithm execution graph. It represents the minimum time needed if executed using infinity processor, and also it used to measure the overall computational effort of the algorithm. So basically, span is the length of the critical path, the longest change of the dependent step, and it shows the minimum time needed if you had infinity processors. Basically, it's the best case parallel time. So remember, if word on parallel search, just remember total effort, and for the span, it's a faster time possible. Both matter when designing efficient parallel algorithm. So that's all for me. I will pass to another partner members. So that's all for me. Thank you.
In this video, I will show you how to calculate work, span, and parallelism in parallel merge sort. Using my own hypothetical scenario, we will sort an array with 8 elements, which are 9, 4, 7, 2, 6, 3, 1, and 5. Parallel merge sort splits the array, sorts part in parallel, and merge them together. The formulas we will use are: first, work equals n times log base 2 of n, and span equals log base 2 of n, and we will substitute n with 8, since we have 8 elements in our array. On to the next slide. Let's calculate total work, which counts all operations. I already prepared the example in the slide behind me. At level 1, we have 4 merges of 2 elements each, so that is 8 operations. At level 2, 2 merges of 4 elements, again 8 operations. At level 3, 1 merge of 8 elements, that is another 8 operations. Add them together and we get 24 operations in total. This matches the formula for work, which is 8 times log base 2 of 8 equals, which we will get the exact number again, which is 24 operations. Now, let's calculate the span, the number of steps on the longest chain of dependent operations. With 8 elements, the array is split 3 times until we reach single elements. And then, we will merge them back 3 times until we get sorted array of 8 elements. So, the span is 3, which matches the formula log base 2 of 8 equals 3. Now, we are at last calculation, which is parallelism. Parallelism is work divided by span. We divided 24 by 3, which gives us 8. That means our algorithm can be up to 8 times faster if run on a system with ideal parallel processing.
Hi everyone, my name is Muhammad Nasrullah. Today I will explain this merge sort diagram. As we can see in the diagram, the algorithm goes top down to divide and bottom up to merge. First, we divide it into 2 halves, left and right. Then we keep dividing each part until every element stands alone. Next, we begin the merge phase. Combine each pair in sorted orders. For example, 9 and 4 become 4 and 9. Then we merge larger sorted arrays like 4 and 9 and 2 and 7 into 2, 4, 7, 9. And on the other side, 3, 6 and 1, 5 become 1, 3, 5, 6. Finally, we merge both halves into the fully sorted list. 1, 2, 3, 4, 5, 6, 7, and 9. Merge sort has a time complexity of n log n, making it faster than bubble or insertion sort of large input. This shows how merge sort use divide and conquer to sort efficiently. Thank you.
This is the formula for Amdahl law. It's calculate the speed up when using multiple processor. In the formula, F represents the fraction of the work that can be parallelized, and 1 minus F is the part that must be done sequentially. To understand parallel performance, we need to look at two key terms. Work T1 is the total number of operations if everything is done sequentially. Span T infinity is the longest chain of dependent step, also known as the critical path. The best possible speed up is calculated by dividing T1 by T infinity.
In this case, we use parallel merge sort algorithm with 8 elements. The total work is 24 operation and the span 3 circular step. From this, we calculated the parallel fraction as 0.875 and the serial fraction as 0.125. This tells us that 87.5% of the work can be done in parallel, while 20.5% must still be done sequentially. In this final slide, we calculate the serial fraction using the formula, then we get the parallel fraction. F equal 1 sub 0.125 equal 0.875. This means 87.5% of the algorithm is parallelizable. Amdahl law shows us the maximum speed up achievable. No matter how many processors we add, the serial part limit the performance. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad bin Muhammad 084029. So as we know, even with infinite processors, the algorithm can run faster than 8 times due to the 3 sequential steps. This serial span becomes a bottleneck, especially as more processors speed up the parallel part. To scale better, it's crucial to minimize both total work and span. So I'm here today to cross-reference this idea with performance consideration and shared framework to explain how overhead and synchronization impact the practical speed up of the algorithm. So this is the factors that often reduce actual speed up compared to the ideal. First of all, we have task management overheads. Thread creation and coordination add overhead, especially in algorithm like parallel merge sort. For small inputs, parallelism can hurt performance. And the next one is synchronization delay. Some step must wait for other to complete. As example, merging in merge sort, barrier, and lock slowing down. Moreover, resource contention. Multiple threads compete for CPU, memory, and cache, causing delay and reduced throughput. And lastly, scalability limit. More processor doesn't always mean more speed. Amdahl's law shows diminishing returns due to unavoidable serial execution and system overhead.
For reflection, my opinion, understanding work, span, and the critical path is key to optimizing parallel algorithm. Work is the total effort needed. Span is the longest chain of steps that must be done one after another. This set the faster time we can finish no matter how many processors we have. The critical path shows where the real bottleneck is.